Hello students, welcome to the class. So in the previous class, we have discussed about the hybridization. We have seen different examples for hybridization. Yes, we have seen the types of hybridizations wherein we have come across sp hybridization, sp2 hybridization, sp3 hybridization, sp3d hybridization, sp3d2 hybridization, and last one is sp3d3 hybridization. Yes. So we have seen the geometry for sp is linear, sp2 is trigonal planar, sp3 is tetrahedral, sp3d is trigonal bipyramidal, sp3d2 is octahedral, sp3d3 is pentagonal bipyramidal. These are the geometries what we have seen. Okay, now I have told you we can predict the type of hybridization using certain formula. H is equal to half V plus M minus C plus A. Suppose I have certain molecules and I want to predict the type of hybridization into that particular molecule. So in the yesterday's class C2H6, I had taken the example. So H is equal to half valence electrons on a carbon. There are 4 valence electrons plus. In the structure, carbon is bonded, both carbons. See, I'll show you the structures. Yes, they are bonded to 3. Each carbon is bonded to 3 hydrogens through a single bond and 1 carbon through a single bond. So how many? Total 4. Minus charge on cation is 0, charge on anion is also 0. So 4 plus 4 is 8. 2 4s are 8. So 4. H is equal to 4 means what? What type of hybridization? 4 hybrid orbitals. It is sp3 hybridization. So it will show sp3 hybridization. Similarly, you can do it for all of them and you can check it. For example, if you have example, say, let me say we will take PCl5. Okay, so phosphorus, H is equal to half. Valence electrons on phosphorus are 5 plus phosphorus is bonded to 5 atoms minus 0 plus 0. 5 plus 5, 10. It is 5. So it is 5. 5H is equal to 5 means what? It is sp3 dehybridization. It belongs to sp3 dehybridization. Yes or no? So this is how we can predict the hybridization of the different molecules as we have discussed in our previous class. So types of hybridizations we have seen sp, sp2, sp3, tetrahedral geometry. Can you see here? See here. This is the example C2H6 ethane. Yes. So if you can observe here, if you can try to connect whatever I have explained. See here. These are the 4 sp3 hybrid orbitals of one carbon, 4 sp3 hybrid orbitals of other. Yes, all 4 are involved in hybridization. Therefore, sp3 carbon of sp3 hybrid orbital of one carbon overlaps actually with sp3 hybrid orbital of another carbon and forms carbon-carbon sigma bond. Remaining 3 sp3 hybrid orbitals, they will overlap with s orbitals of hydrogen and they will form carbon-hydrogen sigma bonds. Yes, so there is one carbon-carbon sigma bond. This is there, and there are 3 carbon-hydrogen sigma bonds for each carbon. Okay, then there are no other unhybridized p orbitals. So you'll get the structure like this. This is 3-dimensional view of ethane molecule. 3-dimensional view of ethane molecule, right? So you can have weave a structure here. Next, ethene molecule. See, carbon. There are 3 sp2 hybrid orbitals. Can you see here? There are 3 sp2 hybrid orbitals. This is one, this is another, and this is another for each carbon. Yes, this is ethene, C2H4. Okay, so the hybrid orbital, sp2 hybrid orbital of one carbon overlaps actually with sp2 hybrid orbital of another carbon to form carbon-carbon single bond. Now, each carbon is having 2 sp2 hybrid orbitals, correct? I'm sorry, here. Each carbon is having 2 sp2 hybrid orbitals. Yes, these are unhybridized. Each carbon is having 2 sp2 hybrid orbitals. They will overlap with s orbitals of hydrogen. Yes, so they will form carbon-hydrogen sigma bonds. How many? 4. Correct? So can you see this? Carbon-hydrogen sigma bond, carbon-hydrogen sigma bonds. Then each carbon is left with unhybridized p orbitals. These are unhybridized p orbitals. Yes, they are parallel to each other. So they will overlap laterally and form what? They will form carbon-carbon pi bond. Carbon-carbon pi bond. So this is sigma, this is sigma. Can you see there is carbon-carbon sigma bond? Then this is carbon-carbon pi bond. Always remember, all hybrid orbitals, they will overlap to give sigma bonds only. The unhybridized orbitals will give pi bond. Unhybridized orbitals will give pi bond. Yes. So this is the structure, orbital view diagram for ethene molecule. This is unhybridized, which are parallel to each other. Yes, rest all. See here, hydrogen overlapping with hydrogen. And this is sigma bond, carbon, carbon. This is carbon, hydrogen, sigma bonds. Is that clear? Yes. And this is ethyne molecule. This is ethyne molecule. See, there are only two. This red color, what you are seeing, they are the two sp hybridized orbitals of carbon. So sp hybrid orbital of one carbon overlaps actually with sp hybridized orbital of one another carbon to form sigma bonds. Here, sp sigma bond. Each carbon is left with one sp hybrid orbitals. They will overlap with s orbitals of hydrogen and form. So here carbon carbon sigma bond is formed. Carbon, which is sp hybrid orbitals, and hydrogen sigma bond is formed. How many? Two. Now each carbon, can you see these green parts? They are having two unhybridized p orbitals. This is one, this is another, which are parallel to each other. This is one, this is another, which are parallel to each other. So these two are parallel to each other and these two are parallel to each other. So they will overlap axially, they will overlap laterally to form carbon unhybridized p orbital will overlap axially with carbon another unhybridized p orbital to form how many? To form two pi bonds. So between carbon and carbon, there is one sigma bond and remaining two are pi. And these two are carbon hydrogen sigma bonds. And the structure comes out to what? It comes out to linear structure. Yes. So this is the orbital diagram for ethyne molecule. Is that right? Yes. Okay. Now sp3d. Now see, example PCl5 or PF5 you can take. Phosphorus ground state configuration is this. In the excited state, one electron from S jumps into D. So P is filled, it will jump into D. So in 3p, there is 3d orbital also. So one electron from 3s jumps into D. See here. So sp3d. All of them undergo hybridization, intermixing and form sp3d hybrid orbitals. How many? 1, 2, 3, 4, 5 hybrid orbitals are formed. And they'll be directed towards trigonal, 3 orbitals in one plane and one above, one below. Yes. So this above and below, they are called axial orbitals. What they are called? This what you are seeing. These are axial hybrid orbitals, this and this. Whereas these which are lying on the in a plane, they are called equatorial. Yes, the bond length of axial is more than equatorial. Can you see? This bond length is more than equatorial. Yes, so they will form a structure like this, which is called trigonal bipyramidal geometry, sp3d hybridization. See here, trigonal bipyramidal geometry with bond angles. Some of them, these form the bond angle of 90 and here it is 120. Trigonal bonds will form 120 degrees and axial form bonds will form 90 degrees. You can view the structure. This is three-dimensional structure. Okay, then this is octahedral. This is for sp3d2. Yes, see SF6. Yes, it will involve the electrons sp3d2, that is s electron 1, p3 electrons and d 2 electrons are involved. So it will form octahedral geometry. Yes, this is in plane, one above and one below. So octahedral geometry is being formed. This is octahedral geometry. sp3d3. It involves intermixing of 7. See, 3 plus 3, 6, 6 plus 1, 7. 7 orbitals. 1s, 3p and 3d orbitals. You can see here. Iodine IF7 is taken as example. Iodine in ground state, it will be having 2s2, 2p7, 2p5, right? Yes. Excited state, what will happen? The electrons which are paired, they will all occupy unpaired. See, one electron from here goes to D, one electron from P goes to D, one electron from P goes to D. So two electrons which are paired here, they will go into D and one electron from S also goes into D. So yes, P3, D3. This is excited state. This is excited state. And all of them are involved in hybridization. Therefore, it forms what? sp3, D3 hybrid orbitals. Yes, and they are directed towards, see, by a pentagonal, this is formed, plane is formed, and one above, one below. So pentagonal bipyramidal geometry. Yes, pentagonal bipyramidal geometry. Equatorial bonds are always longer than axial bonds. I'm sorry, these are equatorial bonds and these are axial bonds, which come in a plane are axial, and above and below comes the equatorial bonds. This is the example for sp3, D3 hybridization. Yes, okay. So moving to the next one, that is molecular orbital theory. In order to understand this molecular orbital theory, let us first try to understand how molecular orbitals are formed. See, when atomic orbitals combine, they will form a new orbitals which are called molecular orbitals. How many atomic orbitals are combining, that many molecular orbitals are formed. Yes, just now what we discussed was hybridized orbitals. Those are when there is intermixing. Here I am speaking about combination. Okay, so when the number of atomic orbitals combine, the same number of molecular orbitals will be formed. Okay, so this is explained by LCAO concept, linear combination of atomic orbitals. The formation of molecular orbitals can be explained by linear combination of the atomic orbitals. Combination takes place either by addition or subtraction of wave function. Now we know that in Schrodinger's wave equation, we used to denote what? We used to denote wave function. We used to denote wave function as psi, right? We used to denote it as psi. This is nothing but wave function. Yes, and we know it is not significant because what is this wave function? It only tells us about the amplitude of the wave. It tells us about this amplitude, height of the crest or depth of the trough. It tells us only about the amplitude of the wave. So combination takes place by addition or subtraction of the wave functions. Now, how to explain addition of wave function? See here, you have taken one wave. This is psi A. Another wave, this is psi B. Both are positive. Yes, both are positive. So what addition of wave function when you write? You will write it as psi is equal to psi A plus psi B. This will be the output. How do we write subtraction? This is psi A and this is psi B. Subtraction of the wave function is written as psi star. Addition is written as psi. Subtraction is written as psi star. So psi star is equal to psi A minus psi B. When you do subtraction, you will get a lower wave. Amplitude will be less. So this is about addition of wave function, subtraction. You just need to remember this. Yes, this doesn't have anything to do with our concept. What I want to say here is when addition and subtraction of the wave functions take place, as I said, how many atomic orbitals are combining, that many molecular orbitals will be formed, correct? So if two atomic orbitals are combining, how many molecular orbitals will be formed? Two molecular orbitals will be formed. One will be formed with addition of wave function. Another will be formed with subtraction of wave function. So I'll just show you here. You can see. So two atomic orbitals are combining. Both the cases. Both are same only. So when two atomic orbitals are combining, it will undergo addition. See, plus plus. It will undergo addition and form one molecular orbital. And the same atomic orbitals, they will combine and they will undergo subtraction, plus minus. Can you see it? And they will form another molecular orbital. So two atomic orbitals are combining. Two atomic orbitals are combining. Two molecular orbitals are formed. Correct? And those molecular orbitals, they are having names. Bonding molecular orbitals and anti-bonding molecular orbitals. So how are bonding molecular orbitals formed? Bonding molecular orbitals are formed by addition of wave functions. And anti-bonding molecular orbitals are formed by subtraction of wave functions. That's it. You need to remember this. And this is called linear combination of atomic orbitals. Understanding? So linear combination of atomic orbitals says that combination of the atomic orbitals, it takes place either by addition or by subtraction of the wave functions. Okay. Second point, how many atomic orbitals are involved? Same number of molecular orbitals will be formed. So if two atomic orbitals are involved, two molecular orbitals will be formed. Yes. What is the third point? What are the types of molecular orbitals formed? The types of molecular orbitals formed are bonding molecular orbitals and anti-bonding molecular orbitals. How are bonding molecular orbitals formed? Bonding molecular orbitals are formed by addition of wave functions. Anti-bonding molecular orbitals are formed by subtraction of the wave functions. Subtraction of the wave function. So this is about linear combination of atomic orbitals, right? Linear combination of atomic orbitals. Okay. So the molecular orbital formed by addition of atomic orbitals is called bonding molecular orbital, which is abbreviated as BMO. While the molecular orbital formed by subtraction of the atomic orbitals is called anti-bonding molecular orbitals. What are the conditions for combination of atomic orbitals? The combining atomic orbitals must have almost equal energy. The combining atomic orbitals must have same symmetry about the molecular axis. The combining atomic orbitals must overlap to maximum extent. They must overlap to maximum extent. Okay. Types, even in like how in atomic orbitals we have types, same in molecular orbitals we have types. Sigma molecular orbitals and pi molecular orbitals. Sigma molecular orbitals are symmetrical around the bond axis. Pi molecular orbitals, they are not symmetrical because of presence of positive lobes above and negative lobes below the molecular plane. Negative lobes below the molecular plane. So we write them as sigma molecular orbitals and pi molecular orbitals. They are represented like that. So sigma molecular orbitals and pi molecular orbitals are considered. Okay, fine. Electronic configuration. Now see, when I was giving you examples of, we have seen different examples for writing electronic configurations of elements, right? 1s2, 2s2, 2p6, 3s2, like that we have seen. Now, how to write the electronic configuration for molecules? Even for molecules, we can write the electronic configuration. Yes, we can write the electronic configuration for the molecules also. This is based on molecular orbital theory. It is based on what? Molecular orbital theory. Okay, let us try to understand. Which is abbreviated as MOT. Okay. Okay. This was being given by Hund and Mulliken. These two people in the year 1932, they gave this. Okay. What are the main ideas of molecular orbital theory? When two atomic orbitals combine, or I may say they may overlap, they lose their identity to form new. Here it is combining. Okay, students. Hybridization, it was intermixing. Fine. So when two orbitals combine, atomic orbitals are combining. I've shown you when two atomic orbitals, they come nearer, their valence orbitals will combine or they will overlap. They lose their identity and form new orbitals. The new orbitals formed are called molecular orbitals. Yes, so you can write them as MO, molecular orbitals. Second point, molecular orbitals are the energy states of a molecule. Like how atomic orbitals are the energy states of the atoms, like that molecular orbitals are the energy states of the molecules, in which electrons of the molecules are filled as just atomic orbitals are the energy states. How you fill atomic orbitals as energy states, how you fill electrons into the energy levels for atoms, similarly you will fill the electrons into the molecular orbitals for molecules. Okay. In terms of probability distribution, when you speak about probability distribution, molecular orbital, it gives us electron probability distribution around the group of nuclei. Electrons probability, it is around a group of nuclei, because in a molecule we have two nucleus. So we say around a group of nuclei. How in atomic orbital? It is around the nucleus, single nucleus. Yes or no? I hope you are getting my point. Fine. So let me say these are the two atomic orbitals combining. So atomic orbital, and it will give rise to two molecular orbitals, right? Addition of if there is addition of wave functions, then it will give me bonding molecular orbital, and if there is subtraction of wave function, it will give me anti-bonding molecular orbital. In bonding molecular orbital, this is the nucleus, and in anti-bonding orbital, this is the nucleus. Okay. So electrons, in case of these are molecular orbitals. Like how in atomic orbitals, electrons are revolving around the nucleus. Similarly, in molecular orbital, the electrons are revolving around the group of nuclei. They are revolving around the group of nuclei like this. Similarly here, they are revolving around the group of nuclei like this. Getting around the group of nuclei. Only those atomic orbitals can combine to form molecular orbitals which have almost same energies, and there should be proper orientation. You cannot make any atomic orbitals to combine and form molecular orbitals. Only those atomic orbitals can combine which have comparable, almost same energy and proper orientation. Their orientation must be proper. Okay. Now, the number of molecular orbitals formed is equal to number of combining atomic orbitals. Two atomic orbitals, two molecular orbitals. Yes, when two atomic orbitals combine, they form two molecular orbitals which are called bonding molecular orbital and anti-bonding molecular orbital. Yes or no? Just now we have seen. The bonding molecular orbital, please remember, the bonding molecular orbital has lower energy than anti-bonding molecular orbital. Not only in anti-bonding, bonding molecular orbitals have lower energy than atomic orbitals also. So I will show you the energy level. Bonding molecular orbital, it has lower energy than atomic orbitals. atomic orbitals have lower energy than anti-bonding molecular orbitals. So which is having more energy? Anti-bonding molecular orbitals are having low energy. So when you are showing energy in this manner, first should come bonding molecular orbitals, then comes atomic orbitals, and then comes anti-bonding molecular orbitals. Please do remember this format, okay? Increasing order. The bonding molecular orbitals, they are represented as sigma, pi, and so on. Anti-bonding molecular orbitals, they are represented as sigma star, pi star, and so on. So bonding molecular orbitals, sigma, pi. Anti-bonding molecular orbitals, sigma star, pi star. The shapes of the molecules depend upon the combining atomic orbitals. Okay. Now, how to fill the electrons? See, filling up of the electrons into the orbitals is same as you fill the electrons in atomic orbitals. You follow Aufbau principle, you follow Pauli's exclusion principle, you follow Hund's rule of maximum multiplicity, correct? Similarly, here also when you are filling the atomic orbitals, you will follow all those three rules. Yes, I will show you the general order. This much you understood? Yeah, you understood all of them. This is very important. They have lower energy than atomic orbitals, have lower energy than antibonding molecular. So this is the energy level. Bonding molecular orbitals are represented as sigma pi. Antibonding are represented as sigma star pi star. Okay. Now how to write the, see for elements, how we used to write? 1s. If 2 electrons are there, 2 will write. Then 2s, 2p, 3s, 3p. Like this you used to write, right? Similarly, for molecular orbitals, how you'll write? The electrons are filled in the increasing order of molecular orbitals, Aufbau principle. Electrons are filled in increasing order of molecular orbital energies. Correct? How the energies increase, like that you will feel. And that order I will show you, general order. The general order is, there are two general orders. If the atomic number is equal to or less than 7, that is up to nitrogen molecule, because molecular orbital, right? Up to nitrogen. How you will fill the electrons? Sigma, okay, I'll take different color to make it a bit interesting to view. Okay, so first lowest energy is sigma 1s. Sigma is written and as a subscript 1s is written. Then next is, this is bonding, sigma star 1s, anti-bonding. Sigma 2s, sigma star 2s. Then pi 2px equal to pi 2py. That means these two have same energies. Then comes sigma 2pz. After that, pi star 2px equal to pi star 2py. Then we have sigma star 2pz, and so on. It continues. Okay, this is for atomic number up to nitrogen, less than 7 or equal to 7. Okay, next is how to write the electronic configuration for molecular orbitals if the atomic number is greater than 7. That is from oxygen, fluorine, if you want, right? How to write it? Okay, there is not much difference. You can see here, I'll write lowest energy orbital is 1s, sigma 1s. Then comes sigma star 1s. Then sigma 2s, sigma star 2s. Then we write sigma 2pz. Then pi 2px equal to pi 2py. Then pi star 2px equal to pi star 2py. And last, sigma star 2pz. Understanding what is the difference? The difference comes only here. Only in this case. So here pi 2px equal to pi 2py will come first and then sigma 2pz. And here sigma 2pz will come first, and then pi 2px, pi 2py. That means that will have lower energy. So you are going to fill the electrons like this. Suppose like how, for example, if you had taken beryllium, atomic number is 4. So the order was 1s, 2s, 2p like that. So what you used to do, you will put 1s, 2 electrons in first 1s orbital, then 2 electrons in next higher energy orbital. Then it was filled. So you used to stop it here only. Similarly, if you have a molecule, what you will do? First you will fill it in lower energy molecular orbital, then you will go on filling it in higher energy. Yes, up to nitrogen, this order is followed. Pi 2px, pi 2py, they will have same or energy and they will come first, then sigma 2pz. For higher than atomic number 7, sigma 2pz comes first, then pi 2px, pi 2py. I will show you here molecular orbital diagram we have. Let's first discuss this. The distribution of electrons among various molecular orbitals is called electronic configuration of a molecule, like how we have electronic configuration of atom. The total number of molecular orbitals formed will always be equal to total number of atomic orbitals offered by the bonding species. There exist different types of molecular orbitals: bonding molecular orbitals, anti-bonding molecular orbitals, non-bonding molecular orbitals. Of these anti-bonding molecular orbitals, we have higher energy than parent orbitals, whereas bonding molecular orbitals will have lower energy than parent orbitals. So first comes bonding, then non-bonding, that is our atomic orbitals, and then we have anti-bonding molecular orbitals. The electrons are filled into molecular orbitals in the increasing order of the orbital energy, from orbital energy lowest to orbital energy with highest energy. Most effective combination of atomic orbitals for formation of molecular orbitals occurs when the combining atomic orbitals have almost similar energies. So NB represents what? Number of electrons occupying bonding molecular orbitals. Na stands for what? Number of electrons occupying anti-bonding molecular orbitals. Please do remember this. Nb means number of electrons in bonding molecular orbitals. Na means number of electrons in anti-bonding. If Nb is greater than Na, then molecule will be stable. Because Nb means what? Bonding molecular orbitals, and they are all what? At lower energies. So if number of bonding molecular orbitals are more, then molecule will be stable. If number of anti-bonding molecular orbitals are more, then molecule will be unstable. Please do remember this point. Okay. Before going to this slide, we'll first see. See, this is called molecular orbital diagram. This is called molecular orbital diagram. You can see here. So lowest, these are atomic orbitals. When I take examples, you'll get to know. This is bonding molecular orbital, and this is sigma star 1s, anti-bonding molecular orbital. Yes. So first, which is the lowest energy? Sigma 1s. Then comes what? Sigma star 1s. Then comes what? Can you see here? Here. Sigma 2s. Then sigma star 2s. Then pi 2px, pi 2py. These two, pi 2px and pi 2py, both have got what? They have got same energy. So I've written them. They are one beside each other. Then comes what? Sigma 2pz. You can keep them sigma 2p only. Okay. So this is x and this is y. This is z. Above that is what? Pi star 2px, pi star 2py, and then comes sigma star 2pz. So this is in the order of increasing energy. Can you see here? Yes. And how many are required for writing the molecular orbitals? We will use that many only. For every molecule, we are not going to write all this diagram. And in case this is for atomic number equal to 7 or less than 7. Up to nitrogen. If it is greater than 7, then what will happen? This particular block will come up and this block will come down. That's it. This will come up and this will come down. Is that clear? So you can visualize here. See here. Molecular orbital energy level with greater than 7. See, for sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, greater than 7. Sigma 2pz came first. Then pi 2px, pi 2py. Then pi star 2px, pi star 2py, sigma star 2pz. If it is less than 7 or equal to 7, sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2px, pi 2py came first. Then sigma 2pz is there. Then we have pi star 2px, pi star 2py, sigma star 2pz. So this is the only change what we are seeing. Yes or no? Here, if it is less than 7, pi 2px, pi 2py is having lower energy. Then sigma 2pz. If it is more than 7, sigma 2pz is having lower energy than pi star, pi 2px and pi 2py. That's it. Okay. So we will take one example. Let us consider one example. What if I want to write, so this is clear to you all? Okay. What if I want to write electronic configuration for hydrogen molecule? How can I write the electronic configuration for hydrogen molecule? See, we are not only going to write the electronic configuration for hydrogen molecule, we are going to predict so many things there. Okay, I'll tell you what all. Atomic number of hydrogen is what? 1. Okay, fine. So if atomic number of hydrogen is 1, that means 1 electron. Hydrogen there are 2. That means how many electrons are there? 2 electrons. Okay. First, better you draw the molecular orbital diagram. Then you can understand. Better draw the molecular orbital diagram. Then you will understand the electronic configuration. Or if you don't want to draw the molecular orbital diagram, directly you can write the electronic configuration. Fine. Okay. So these are the 2 hydrogen atoms. This is one hydrogen atom. This is another hydrogen atom. They are going to combine. Correct. So this hydrogen atom is having 1s, 1 electron. This also is having 1s, 1 electron. Correct. Okay, fine. So they will combine to give lower energy orbital, which is called what? Bonding molecular orbital. And they will also combine to give higher energy orbital, which is called anti-bonding molecular orbital. Okay. So there is one. So this is atomic orbital. This is also atomic orbital. I want 2 hydrogen atoms, so I've taken 2 hydrogen atoms. And these are what? Molecular orbitals in the increasing order. See, bonding molecular orbital is having lower energy than atomic orbitals, which is having lower energy than anti-bonding molecular orbitals. Okay. So 1s1 means what? There is 1s1 means what? There is 1 electron. Correct. And here also 1s1 means there is 1 electron. So both of them will combine and come where? They will first occupy the lower energy orbital. Correct. They will first occupy the lower energy orbital. And that is represented how? Sigma 1s. And this is what? Anti-bonding sigma star 1s. Correct. So first it will occupy lower energy orbital. So lower energy orbitals, it will get paired. Only when this is filled completely, you have to go to higher energy orbital. That is anti-bonding molecular orbital. So they will come and occupy here. How many electrons are there in atomic orbitals? Totally 2. And 2 are filled. So there is nothing to be filled here. Therefore, how to write the electronic configuration? Electronic configuration of hydrogen molecule is what? I will write the electronic configuration of hydrogen molecule as sigma 1s with the 2 electrons. Therefore, I'll mention here sigma 1s 2. Sigma 1s with 2 electrons. Yes. So this is the configuration for hydrogen molecule. Looking at the configuration, you can speak. Now tell me, number of electrons in bonding molecular orbital, it is represented as NB. Number of electrons in bonding molecule. How many? It is 2. Number of electrons in anti-bonding molecular orbitals, it is represented as Na. How many are there? 0. Yes. Why I'm saying this is, using this information, we can find so many things. We are not only going to write the electronic configuration or draw the molecular orbital diagram, we are going to find so many things here. What we are going to find? Yes, see here. First, what we are going to find is, we are going to find the bond order. So we already know it is number of bonds between the 2 atoms. How to find it? I had told you there is a formula. Bond order is equal to half NB minus Na. Half NB stands for what? Number of electrons in bonding molecular orbital, minus Na stands for what? Number of electrons in anti-bonding molecular orbitals. When you do half of it, you will get the bond order. The bond order may be whole number, it may be fraction, it may be also 0. It may also have positive or negative value. We'll see when we come across certain things, certain ions, will get this answer. Okay. So can I calculate the bond order here? Therefore, bond order is equal to, tell me the bond order. Bond order is equal to half minus number of electrons in bonding minus number of electrons in anti-bonding. So that is equal to half. Bonding, there are 2 electrons, minus 0. So it is 2 minus 0 is 2. 2 ones are 2 ones are. So bond order is equal to 1. What does bond order equal to 1 means? Bond order equal to 1 means there is a single covalent bond in hydrogen molecule. there is a single covalent bond in hydrogen molecule. So bond order is 1, single covalent bond. Yes, even you can speak about the magnetic properties. Yes, so nature of the bond, integral bond order value for single, double and triple bonds will be 1, 2 and 3 respectively. So if the bond order is 1, it is single covalent bond. Bond order is 2, double covalent bond. Bond order is 3, triple covalent bond. Bond length. Bond order is inversely proportional to bond length. As bond order increases, the bond length decreases. Thus, greater the bond order, smaller will be the bond length. Magnetic properties. You can speak whether the given molecule is paramagnetic or diamagnetic. Now, what do we mean by diamagnetic? If all the molecular orbitals have paired electrons, the substance is diamagnetic. If one or more molecular orbitals have unpaired electrons, it is paramagnetic. So diamagnetic and paramagnetic nature, you are going to look at the molecular orbitals and say whether it is diamagnetic or paramagnetic. Now you can see here, this is the molecular orbital. Yes. Is it paired? Is it having paired electrons or unpaired electrons? Yes, both the electrons are paired. So in this orbital, the electrons are paired. And this is the only configuration for hydrogen. So since the electrons are paired in its orbital, it is what? It is diamagnetic. It is diamagnetic. Yes. If there was unpaired electron, then it would be paramagnetic. Yes. If there was unpaired electron, it would be paramagnetic. Yes. Similarly, you can take the example. Second example, you can take it for helium. Helium molecule, if I say He2, I know atomic number of helium is 2. So I need 2 helium atoms. So totally how many electrons? 4 electrons. So again, write this orbital diagram. First, try to write the orbital diagram. Once you write this orbital diagram, you can understand the electronic configuration and all the other things regarding the orbitals. So first here, these are atomic orbitals. What I write here is what? It is bonding molecular orbital, and this is anti-bonding molecular orbital. Yes. So they will undergo additive overlap to give bonding molecular orbital, and they will undergo subtractive overlap to give anti-bonding molecular orbitals. This is represented how? You represent it as, this is 1s with 1s and this is 1s. This is sigma 1s. This is sigma star 1s, correct? So sigma 1s, that is bonding molecular orbital. Sigma star 1s, anti-bonding molecular orbital. Now you know that in helium configuration, atomic orbital, it is 1s2. So I will write 2 electrons here, and same with here, another helium atom, 2 electrons. So when they overlap, first bonding molecular orbitals are filled. So first lower energy orbital gets filled. Once this orbital gets filled, are there any free electrons? Yes, of course, there are 4 electrons and only 2 are filled here. And remaining 2 will occupy where? They will occupy anti-bonding molecular orbitals. Therefore, I can write how here, I'll write sigma 1s2, and sigma star is also having 2 electrons. So sigma star 1s2. Is that right? So using this, write the electronic configuration. Very simple. Electronic configuration of helium molecule. Yes, helium molecule is, what is the electronic configuration? How do we write it? First, lower energy orbital, sigma 1s having 2 electrons, then sigma star 1s also having 2 electrons. So this is the configuration for helium molecule. Now, how many electrons are there in bonding molecular orbital? There are 2 electrons. How many electrons in anti-bonding molecular orbital? There are also 2 electrons. Calculate the bond order. Bond order is equal to, what is the formula for bond order? It is half number of electrons in bonding, that is 2, minus number of electrons in anti-bonding, that is 2. 2 minus 2 is what? 0. 0 by something is what? 0. So bond order is 0 means what? That means there is no bond between the 2 helium atoms. There exists no bond. So how do I say? Bond order is 0 means there exists no bond between 2 helium atoms. Therefore, I say helium is monoatomic molecule. Understood? In one of few of our slides we were discussing last videos, I was continuously saying noble gases are monoatomic molecules. That means they have independent existence as a molecule only, because bond order is 0. There is no bond between 2 helium atoms. And how do we explain it? We explain it by molecular orbital theory. We explain it by molecular orbital theory. So bond order is 0. Now coming to the magnetic properties, whether they are paramagnetic or diamagnetic. Diamagnetic means what? All the molecular orbitals should be filled. There must be no unpaired electrons, then it is diamagnetic. Paramagnetic means what? If there is at least one unpaired electron. Now see here, this orbital is also filled with 2 electrons. This is also filled with 2 electrons. Therefore, helium molecule, I'll write helium molecule like this now. It is what? It is diamagnetic because there are no unpaired electrons. There are no unpaired electrons. So if you observe here, here is the example, hydrogen molecule. So this is homonuclear, that is what? Having same atoms, right? So we have for our study here only homonuclear, that is diatomic molecules. So combination of 2 hydrogen atoms, each hydrogen atom has 1 electron in 1s orbital. So the electronic configuration of hydrogen molecule becomes sigma 1s2. So bond order, as we have calculated, it is half. Bonding electrons are 2 minus 0, it is 1. We have seen this, right? So this indicates that 2 hydrogen atoms are bonded by a single covalent bond. The bond dissociation energy of hydrogen has been found to be 438 kilojoules per mole. That means to break the hydrogen bond in hydrogen molecule into 2 hydrogen atoms, how much energy is required for 1 mole to break 1 mole of hydrogen bonds? A bond between hydrogen atoms, I need 438 kilojoules of energy. The bond length in hydrogen molecule, it is 74 picometers. That means the internuclear distance between the 2 hydrogen atoms in hydrogen molecule, it is 74 picometers. No unpaired electrons are present. Therefore, the molecule as whole is diamagnetic. Helium molecule. They contain 2 electrons. Thus, in helium molecule would be 4 electrons. Sigma 1s2, sigma star 1s2. Bond order 2 minus 2 becomes 0. Therefore, we say helium molecule is therefore unstable and it does not exist. Now see, lithium molecule. I will show it here only. That would be better for you all to make you all understand. So let us see here, lithium molecule. When we say, I will write it here. Fine. Lithium molecule. So I like 2. Atomic number of lithium is what? 3. If it is 2 atoms, then how many electrons? The number of electrons will be 6 electrons. And I know that configuration of lithium molecule is 1s2, 2s2, 2p1. Correct? It is 1s2 and 2s1. Okay, fine. So lithium molecule has got electrons in 1s2 orbital. So there are 2 electrons. And in 2s, there is only 1 electron. Correct? So there is 1 electron in 2s. Similarly, this side lithium atom also 1s2 and in 2s there is 1 electron. Okay, now we will go on filling the electrons. Okay, fine. So let us fill the electrons now. The first 2 electrons will occupy lower bonding molecular orbital. So they will fill here. So sigma star 1, sigma 1s2. Again 2 electrons are left. They will occupy anti-bonding molecular orbital. So sigma star 1s2. Observe, here there are 2 plus 2, 4 electrons. Here also 4 electrons. So verified. Now 2s is having 1 electron. This 2s is having 1 electron. They will come and occupy the lower energy bonding orbital, that is sigma 2s. So how many electrons? 2. Now, are there any electrons left to occupy anti-bonding? No. So this will be the total end. So what is the electronic configuration of lithium molecule? Starting from lower energy, the electronic configuration will be sigma 1s2, sigma star 1s2, and then sigma 2s2. Sigma star doesn't have, so I will not write it. So how many electrons in bonding? There are 2 electrons here, 2 electrons here. So these are the 2 electrons in bonding, and these are also the 2 electrons in bonding. So 2 plus 2 is how much? 4. How many electrons in anti-bonding? It is 2. So calculate the bond order. Bond order is equal to half. 4 minus 2. Yes, it is 2. 2 ones are 2 ones are. So it is 1. Bond order is 1 means what? That means in lithium molecule, there is a single covalent bond. Are there any unpaired electrons? This is paired, this is paired, this is also paired. So the molecule as whole is diamagnetic. As a whole is diamagnetic. Is that clear? This is about lithium molecule. Similarly, you can write for beryllium molecule also. Instead of 2 here, there will be 2 electrons here. And this 2 also gets filled, this 2 also gets filled. Okay. If I take boron molecule, yes, or let me say I will take a carbon molecule, or we'll go still further, I will consider nitrogen molecule. Atomic number of nitrogen is 7. 2 nitrogen atoms means there will be 14 electrons. Yes, what is the atomic electronic configuration of nitrogen atom? It is 1s2, 2s2, 2p3. So 3 plus 4 is 7, correct? So it is 2p3. So this is for nitrogen atom. So I will fill the electrons here accordingly. So first let us fill the electrons. So 1s2, 2s2, 2p3. So let us fill them. So 1s2, 2s2, 2p3. Spin up, spin up, spin up. Similarly, here also same nitrogen atom. 1s2, 2s2, 2p3. Spin up, spin up, spin up. So there is 2p3 electrons. Correct? Okay. Now we will go for filling up of the molecular orbitals. Now first they will occupy the lower energy orbital, that is bonding molecular orbital. So 2 electrons. Then 2 electrons are left. They will occupy here. So sigma star 2s. Then here these 2 electrons will first occupy lower energy orbitals sigma 2s. Then still electrons are left. They will occupy higher energy orbitals. So sigma star 2s. Now see, pi 2px, pi 2py are having lower energy and they are having same energies. Therefore, this electron and this electron, how they will occupy? Pauli's exclusion, Hund's law of maximum multiplicity. Pairing of the orbitals having same energy will not take place until each orbital is singly occupied. So first one electron will come here, one electron will come here. If electrons are left, are the electrons left? Yes. Then only pairing will occupy. Pairing will occupy. Until and unless these two are filled completely, we cannot go for this. So one electron came here, 1, 1. Second electron came here, second. Now still electrons are left, they will come here. They will come here. Yes, if it was for boron, you see, so boron was having 2p1. So one electron. So it would be like this. Understanding? Are you all getting? Or if you want, I will take it for boron only first. So just imagine that I'm explaining for boron. So boron, what is the, so I'll take it for boron first. I'll make that clear, then we'll go for. So boron is 5, 1s2, 2s2, 2p1. So I've written it like this, right? So the electrons are filled here. Now this electron, 1, 1, 1, 1, they will come like this. So what is the electronic configuration of boron molecule? Lower energy, sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, then pi 2px1 equal to pi 2py1. So same energies, correct? So bond order, number half minus bonding molecular orbital. This is bonding, which are not having star, they are bonding. This is bonding, this is also bonding. 2, 3, 4, 5 and 6. 6 minus 1 electron are there. And here 4. 6 minus 4 is how much? 2. 2 ones are 2 twos are. So 2 ones are 2 ones are. Yes. So bond order is 1 means what? There is a single bond between 2 boron atoms. Correct? Similarly, if you want to write for carbon, I'll show it here only. Yes. Carbon atomic number is 6. So 1s2, 2s2, 2p2 it will be. So if you want it for carbon, how do I write it? So here I can show you 2p2 for carbon. 1 electron, 1 electron. So 2p2. Therefore, what happens when filling? First they will occupy single, then electrons are there, they will be filled. So configuration of any other electrons, 4, 2 to 4, 2 to 4. So there are no electrons. So sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2. Correct? Bond order, half, 2, 4, 6, 8. 8 minus 4. So 8 minus 4 is how much? It is 4. 2 ones are 2 twos are. So bond order is 2 means what? Bond order is 2 means it is having double bond between 2 carbon atoms. One more thing I forgot to say, in case of boron, there were 2 unpaired electrons here. 1, 1 was there, correct? For boron, it was like this. For boron, it was like this, correct? So what is the magnetic property of boron? Boron is having unpaired electrons in its orbital. Therefore, it is paramagnetic. Boron is what? Paramagnetic. Correct? So with this explanation, we will come to nitrogen now. Whereas carbon is what? It is having all filled. So it is diamagnetic. This is diamagnetic. Fine. Now for nitrogen, as we said, it is 2p3. 2p3. Correct? So 1, 1, and here also 2p3, 1, 1. Okay. Now, so 1, 1 electron, then pairing, then still electrons are left. I'll fill here. Any other more electrons? 3 plus 3, 6, 3 plus 3, 6. So what will be the electronic configuration of nitrogen? Starting sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2 equal to pi 2py2, and then sigma 2pz2. Correct? How many bonding electrons? This is bonding, this is bonding, and all these are bonding only. There is no star. So how do you calculate bond order? Bond order is equal to half. How many bonding electrons? 2, 4, 6, 8, 10. Minus anti-bonding are 4. So it is 6, 2 3s are. So bond order is how much? It is 3. That means between two nitrogen atoms, there is a triple covalent bond. There is a triple covalent bond. Understood? Any of the unpaired electrons in any of the molecular orbitals? No. Therefore, nitrogen molecule is diamagnetic. It is diamagnetic. Sometimes what happens, they will not give you nitrogen molecule. They will say N2. They will ask you N2 plus ion. So in this case, what you will do? N2 plus means what? Plus means loss of one electron. So what you will do? You have to remove the electron, and you will remove the electron from the outermost shell. So which electron you will remove? You will remove this electron. Understanding? You will remove this electron. Are you all getting it? So if it is N2 plus, what you will do? If it is N2 plus, then there will be only one electron here, because one electron has to be removed. And configuration will be what? Sigma 2pz1. So can I say N2 plus is paramagnetic? N2 plus is paramagnetic because it is having unpaired electron. N2 is diamagnetic. N2 plus is paramagnetic, and its configuration will be what? Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2, sigma 2pz1. N2 plus. Instead of N2 plus, if they would have said N2 minus, what I would do? I would first write N2. N2 minus means what? Gain of one electron. When it will be gained? It will be gained in the next higher energy level. So it will come here. Yes. Again, it is paramagnetic. Paramagnetic. But the configuration would be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2, sigma 2pz2, pi star 2px1, pi star 2px1. Understanding? So how they have said, like that you will go on adding or removing the electrons. Is that clear? One last example. O2. Yes, I'll not consider this because I know that if the atomic number is more than 7, there is change in this. Okay, so let us consider this one. Is that right? With atomic number greater than 7? Okay, fine. So Z, atomic oxygen, O2 molecule I'm considering. So we know that there are 1s2 electrons, then 2s2 electrons, 2p4, correct? Oxygen. Spin up, spin up, spin up, spin down, 4 electrons. Similarly, 1s2, 2s2, 2p, spin up, spin up, spin up, spin down, 4 electrons. Okay, shall we fill now? First, they will occupy lower energy, then higher energy. So sigma 1s2, sigma star 1s2. Then lower energy, then higher energy. Sigma 2s2, sigma star 2s2. Now, one electron, one electron. First, they will occupy sigma 2pz because that is having lower energy. Then one electron comes here, one electron comes here. So any electrons left? Yes. Another electron comes here, another electron comes here. Total of 6. Here there are 8. Now one more and one more electron. They will occupy here. One electron here, one electron here. Verify. Are we writing correct electrons? 2, 4, 6, 8. 4 here, 4 here. Yes. So sigma 2pz2, pi 2px2, pi 2py2, then pi star 2py1, pi star 2py1. Correct? Write the configuration. The configuration of oxygen molecule will be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, then sigma 2pz2 first, then pi 2px2 equal to pi 2py2, then pi star 2px1 equal to pi star 2py1. Is that clear? I've written this configuration. Calculate the bond order. Half bonding 2, 4, 6, 8, 10. So there are 10 electrons minus anti-bonding. See, this is 2, this is 4, 5 and 6. So there are 6. So 10 minus 6 is how much? 4. 2 ones are 2 twos are. So bond order is equal to 2. That means between two oxygen atoms, there is a double covalent bond. Any of the unpaired electrons? Yes, oxygen has 2 unpaired electrons. Therefore, it is paramagnetic. Okay. Now, what if I would have given you O2 plus? That means loss of 1 electron. You would have removed this electron. You will calculate bond order accordingly. Bond order changes. Yes. So what happens to the bond order? Here there are 6 electrons in bonding. Now here one less. So it becomes 5. So 10 minus 5 is 5. 2. It is 2.5. See, bond order comes in fraction also. If I give you O2 plus 2, I'll remove this electron also. O2 plus 2 is diamagnetic because it is not having any unpaired electrons. Is that right? If I would have given you O2 minus, then these 2 electrons would be there. There would one more electron come here. Yes, bond order would change again. Then O2 minus 2, peroxide ion it is. One more electron would come here. This would be again diamagnetic because there are no unpaired electrons. So O2 plus 2 and O2 minus 2 are both diamagnetic, whereas O2 plus and O2 minus are still paramagnetic. Yes, so you can practice at your home. You can practice it for F2 molecule also. F2 molecule. Is that clear? So this is how we calculate, we do the molecular orbital theory. See, lithium molecule. I've written it. So it is diamagnetic since all the orbitals are completely filled. Oxygen molecule. Just now I have written. Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Then we have sigma 2pz2, then pi 2px2, pi 2py2, pi star 2px1, pi star 2py1. Yes, this can be also written as, see, sigma 1s2, sigma star 1s2, it belongs to K shell. Therefore, I can write it as KK. One for bonding, one for anti-bonding. So KK. Then sigma star, this is not filled. Therefore, I will not write it L. Paramagnetic because of presence of 2 unpaired electrons. Last part, hydrogen bonding. What do we mean by hydrogen bonding? Yes. This hydrogen bonding was for the first time introduced by Latimer and Rodebush scientists in the year 1920. When highly electronegative elements like, see, hydrogen bonding comes only for 3 elements, that is fluorine, oxygen and nitrogen. When highly electronegative elements like fluorine, nitrogen and oxygen are attached to hydrogen, yes, to form a covalent bond, the electrons of the covalent bond are shifted towards more electronegative atom. Okay, let us take this like this only and explain. Fine. Okay. Now see, I have, let me say I have HF molecule, or say I have H2O molecule, or say I have NH3 molecule. So in this case, all are covalent bonds. Yes. So please observe these covalent bonds. Yes, I'm not speaking about hydrogen bond yet. So in these cases, since fluorine is more electronegative, the electrons of this bond are shifted more towards fluorine. Therefore, we know polarity is created in covalent compounds also. So partial negative charges on fluorine, partial positive charges on hydrogen. Similarly, oxygen, partial negative charge, this develops partial positive charge, partial positive charge. Similarly, on nitrogen, partial negative charge because that is more electronegative. All hydrogens will have partial positive charge. Correct? Okay. So if I consider only HF molecule, so there is partial negative charge on fluorine, partial positive charge on hydrogen. If I consider one more HF molecule, which is still having partial negative charge on fluorine, partial positive charge on hydrogen, there is slight attraction between fluorine of one molecule and hydrogen of another because they are having partial charges. So like unlike charges attract. So this small attraction between what? Between hydrogen and most electronegative atoms, say fluorine or oxygen or nitrogen, that is called hydrogen bond. What it is called? Hydrogen bond. This is not hydrogen bond, students. This is purely covalent bond formed by mutual sharing. But because of polarity in covalent bonds, the unlike charges, the hydrogen of one molecule attracts fluorine of the other. Yes, because of slight charges. That slight attraction is called what? Hydrogen bond. Yes, therefore I define hydrogen bond as the bond formed between hydrogen and most electronegative atoms like fluorine, oxygen and nitrogen only. You cannot take HCl and say there is hydrogen bond between hydrogen and fluorine. No, there is no hydrogen bond here. Understanding? So the bond formed between hydrogen and more electronegative atom, fluorine, oxygen and nitrogen, is called hydrogen bond. Here also you can see, if I write one more H2O molecule, this is slightly positive. Therefore, oxygen will pull and form. So hydrogen, there is bond between hydrogen. First, I have to take hydrogen and more electronegative atom of other molecule, oxygen. Yes. So this bond is called what? It is called hydrogen bond. That's the reason, hydrogen bond. Bond between hydrogen and more electronegative atom. More electronegative atom is called hydrogen bond. It is called hydrogen bond. So let us see here, when highly electronegative elements like nitrogen, oxygen, fluorine, they are attached to hydrogen. So thus partial positive charge develops on hydrogen atom, which forms a bond with other electronegative atom. This bond is known as hydrogen bond, and it is weaker than covalent bond because partial negative charge attraction is there. In HF molecule, hydrogen bond exists between hydrogen atom of one molecule and fluorine atom of another. You can see here. Can you see this? HF is there. This strong bond, what you are seeing is what? It is covalent bond. But this dotted line, what you are seeing, it is hydrogen bond. So in HF molecule, when we are representing hydrogen bond, it is always shown in zigzag form. It is shown in zigzag form. This is our hydrogen bond. Whereas this is what? This is strong covalent bond. We have types of hydrogen bonds: intermolecular hydrogen bond and intramolecular hydrogen bond. Intermolecular means what? Between two molecules, like as in HF, this is one molecule and this is another molecule. So between two molecules there is hydrogen bond between hydrogen and more electronegative atom. Similarly in water also you can see there is intermolecular. Oxygen, hydrogen of one molecule, this is one molecule, and oxygen of other molecule. Oxygen of other molecule. So if the hydrogen bond is formed between hydrogen of one molecule and more electronegative atom of other molecule, so if it is between two different molecules, then we call it as intermolecular. Example, HF is intermolecular, NH3 is intermolecular, water is intermolecular. So water forms hydrogen bond with another water molecule. They are called intermolecular hydrogen bonds. Then what is intramolecular? If the hydrogen bond is present within the molecule, see this entire thing what you are seeing, this is one molecule only. Its name is O-nitrophenol. See, there is OH group attached to benzene ring, we call it as phenol, and there is NO2 group at ortho position. I have told you what is ortho position. The next adjacent position is ortho. Therefore, I call it as O-nitrophenol. So you can see here hydrogen of this molecule only is having slight attraction towards oxygen of the same molecule. So hydrogen bond is within the molecule. It is not in between. It is within the molecule. Such hydrogen bond is called intramolecular hydrogen bond. What it is called? Intramolecular hydrogen bond. Yes. So what happens? What are the properties with this intermolecular and intramolecular hydrogen bonding? What are the characteristics? Effects of hydrogen bonding. First point is dissociation. In aqueous solution, if you take HF, there is hydrogen bond between fluorine and hydrogen. So this is hydrogen bond. This is again covalent bond. Yes, it gives us difluoride ion instead of fluoride ion. Why? Because of hydrogen bonding. It will give us HF2 minus instead of HF minus. Understanding? Because of hydrogen bond. Second thing is association. See what happens if many molecules are present. See, I cannot keep only one molecule together, right? So HF will form intermolecular hydrogen because of intermolecular hydrogen bonding. the molecules will come together. So they get associated. So when they get associated with each other, what will happen? Their molecular mass will increase. Their molecular mass will increase. So that is one point, effect of hydrogen bonding. Abnormally, the molecular mass will increase. Abnormally, the molecular mass is increasing. Third point is high melting and boiling point. High melting point and boiling point. Yes. Example, if you see water, I will show you. Water, one molecule of water can form 4 hydrogen bonds. I may say how. Just see here. Oxygen, it is having O2 minus, right? So it will combine with 2 hydrogen atoms of other water molecule. Hydrogen will combine with oxygen of other water molecule. This hydrogen will combine with oxygen. I'm sorry. So this hydrogen will combine with oxygen of other water molecules. So altogether, how many hydrogen bonds are formed? One water molecule, it can form 4 hydrogen bonds. So when all the molecules get associated like this, you need to first break these bonds. So to break these bonds, we need to put more energy. Therefore, melting point and boiling points will increase. Yes, there will be abnormally high melting point. If you look, melting point of water is what? It is, boiling point of water is what? It is 100 degrees Celsius. So all the bonds have to be broken. Then only it will come into vapor state. It will come into vapor state. So extra energy is needed to break the bonds. Not only water, even your HF molecule, even your NH3 molecule. Abnormally high melting and boiling points are there. Solubility. Polar compounds will dissolve in polar solvents. But alcohol, if you take, alcohol is denoted as ROH. This is non-polar. Then still it is soluble in water. The reason is the oxygen, or you can say the oxygen of this alcohol will form hydrogen bond with hydrogen of water. So it will form hydrogen bond. Therefore, it will dissolve in water. Otherwise, this is a non-polar compound. It shouldn't dissolve in water. It should dissolve in non-polar solvents. Why it is dissolving in water? You will come across these questions when we'll discuss about physical properties of the organic compounds. That time you have to answer this. Because of the tendency of forming intermolecular hydrogen bonding, they dissolve in water. They dissolve in water. Volatility character we have. Since there is intramolecular hydrogen bonding, they will not leave the surface that easily. That becomes more volatile. Yes. So intermolecular hydrogen bonding, this is the examples. You can see water molecule, ammonia molecule is there, NH3. Nitrogen of one molecule has formed bond with hydrogen of the other molecule. Intermolecular, intramolecular, O-nitrophenol. Hydrogen of one of the molecule has formed bonding with oxygen of the same molecule. O-hydroxybenzaldehyde. See, OH group is there, CHO group is there. It is called hydroxybenzaldehyde. Hydrogen of the molecule has formed intramolecular hydrogen bonding with oxygen of the same. Yes. So what happens because of this? All the properties get differentiated. Even ice floats on water, but the density of ice is more than water, right? Then why it floats on water? Why ice floats on water? So in case of solid ice, hydrogen bonding gives rise to cage-like structure. Here, it forms a cage-like structure. So because of this cage-like structure, each water molecule will be linked to 4 other water molecules. I have shown you. So due to this, ice will have lower density than water. Ice will have lower density than water. That's the reason ice floats on water. Ice will float on water. On heating, what will happen? On heating, the hydrogen bond starts breaking because that is the weakest bond, right? It will start breaking. Obviously, the molecules are not so closely packed as they are in liquid state. Thus, the molecules come together, resulting in decrease in the volume. And hence, there will be increase in the density. Understanding? So, this goes up to 277 Kelvin. At 277 Kelvin, increase in volume is due to expansion of liquid. And it becomes much more than decrease in the volume due to breaking of hydrogen bonds. Yes, so density of water is maximum at 277 Kelvin. Why ice floats on water? Because water molecules form intermolecular hydrogen bondings, they will get into cage-like structures. So due to that cage-like structure, ice will have lower density than water, and therefore it floats on water. So the reason why ice floats on water is due to hydrogen bonding. So this completes the topic. In the next class, we will take up with the multiple choice questions associated with this topic. Please do practice all the concepts so that it will help us to solve the questions. For now, thank you.